Good evening, all. I welcome you all for the Week 5 live interactive session for the course Chemical Reaction Engineering 2. Now, let's get on to the session. So, as usual, before we get on to the practice assignment session, let's have a brief recap of the lectures of week 6. Week 6 again had 5 lectures. From lecture 26 to 30, where lecture 26 was on estimation of mass transfer coefficient. In lecture 25, the mass transfer coefficient for a single particle without reaction was initiated, uh, uh, where the concentration profile was estimated, and in the lecture 26 this was continued, where the cross-link correlation uh, was discussed. So this cross-link correlation, it is nothing but it is based on your analogy between your heat transfer and your mass transfer. So there are correlations, you can develop correlations. So you can develop correlations where the dimensionless number that matches uh, for a Nusselt number in case of a mass transfer is the Sherwood number, and for a Prandtl number it is the Schmidt number, where your Sherwood number is nothing but your ratio of your convective mass transfer to your diffusive mass transfer, and your Schmidt number is the ratio of your momentum diffusivity to mass diffusivity. So an example problem was also solved based on this concept. And in lecture 27, mass transfer to a single particle with reaction was discussed, where two cases were discussed. Case 1 was when the surface reaction is rapid, while case 2 was on when diffusion is relatively faster. So, based on these two concepts, the mass transfer through a particle with reaction was discussed. And then in lecture 28, packed bed reactor design was discussed with mass transfer limitation, where the correlation was developed between length, superficial velocity, area of contact, mass transfer coefficient, and conversion. In lecture 29, the Theonis-Kramer correlation and Kolben correlation to estimate the conversion in case of packed bed reactors was discussed. In case of packed bed was discussed, and lecture 30 had an example problem being solved based on both the Theonis-Kramer correlation and Kolben correlation. Now, let us move on to this week's practice assignment. So, question number 1. Identify the correct correlation for the Kolben factor JD from the below. So, Kolben factor JD, option A, JD is equal to Reynolds number power 0.5 into Schmidt number divided by Sherwood number, or is it option B, JD is equal to Reynolds number power 0.5, Schmidt number power 1 by 3 divided by Sherwood number, or is it option C, JD is equal to Sherwood number divided by Reynolds number power 0.5 multiplied by Schmidt number power 1 by 3, or is it option D, JD is equal to Sherwood number divided by Reynolds number into Schmidt number power 1 by 3. Which of these is the correct option? So the solution is, the answer is, it is actually option D, where JD is equal to Sherwood number divided by Reynolds number into Schmidt number power 1 by 3. Now question number 2. Based on the Frostling correlation, for a sufficiently large Reynolds number, estimate the change in mass transfer coefficient if the diameter is decreased by 4 times while the velocity is increased by 2 times. Here there should be velocity increased by 2 times. So, does the mass transfer coefficient increase or decrease? So, what is given? Given the diameter of, for the case 2, that is dp2 is equal to 1/4 of dp1, while the superficial velocity u2 is equal to 2 times of u1. So we know the Frostling correlation is Sherwood number is equal to 2 plus 0.6 into Reynolds number power 0.5 multiplied by Schmidt number power 1 by 3. There is one more information given. The Reynolds number is sufficiently large. So in the Frostling correlation, we can eliminate this 2 since the Reynolds number is sufficiently large. So the Frostling correlation becomes now as Sherwood number is equal to 0.6 into Reynolds number power 0.5 multiplied by Schmidt number power 1 by 3. Now, incorporating the individual, formulas for Sherwood number, Reynolds number and Schmidt number we get, where Sherwood number is Kc into dP by dAb, where Kc is the mass transfer coefficient and dP is diameter of the particle and dAb is the diffusivity, is equal to 0.6 into u into dP by nu power 1 by 2, where u is your superficial velocity, dP is your diameter of the particle and nu is your kinematic viscosity, which is given by mu by rho. And your Schmidt number is nu by dAb, where nu is your kinematic viscosity, or it can also be called as momentum diffusivity divided by mass diffusivity, that is dAb, power 1 by 3. Now, so just rearranging the formula, what you get, Kc is equal to 0.6 into dAb power 2 by 3, because this dAb goes to the right hand side. So dAb power 1 minus dAb power 1 minus of 1 by 3, that will give you dAb power 2 by 3. Similar and your nu is there in both these terms. So it is nu power 1 by 3 minus 1 by 2. You will end up with nu power minus 1 by 6. So you bring the nu to the denominator. So it is nu power 1 by 6. And u is, there is only one u term. So you have u power half and dp again. So dp power half minus dp power 1, because this dp goes to the denominator. So dp power half minus 1. So you will end up with dp in the denominator. So dp power half. So now it is given that your only your superficial velocity and your diameter of the particle changes, whereas the rest of the components are the same for both the cases. So upon applying these, you will end up with the equation Kc2 by Kc1 is equal to u2 by u1 power half multiplied by dp1 by dp2 power half. So substituting what is dp2 and u2 in terms of the relation given, you have Kc2 by Kc1 is equal to 2 into u1 by u1 whole power half in multiplied by 4 into dp1 by dp1 whole power 1 by 2, because dp2 is nothing but 1/4 of dp1. So this dp2 is in the denominator. So 1 so dp1 by 1/4 of dp1. So this 4 goes to the numerator. That's why. So you will end up with 2 into 4 the whole power half that is equal to 8 power half. So square root of 8 is 2.828. So you find out that Kc2 is equal to 2.828 of Kc1. That means there is an increase in mass transfer coefficient by 2.83 times compared to the initial mass transfer coefficient when you double the superficial velocity and decrease the particle diameter, double the superficial velocity and decrease the particle diameter by one fourth, provided the other parameters are constant and your Reynolds number is sufficiently high. What would have happened if the diameter of the particle is decreased to half? Then you could find that uh, you know uh, in the second term you will have uh, 2 times of dp1 by dp1, that is nothing but it will be for square root of 4, that is 2 times increase. Whereas if you increase the particle diameter by 2 times, then it will end up with the fact that there will not be any change because your superficial velocity is doubled, simultaneously your diameter is also doubled. So both will cancel out each other because they are inversely related. So you will end up with no change in the uh, mass transfer coefficient. So we have to take a call. So your velocity should be increased while your uh, diameter should be decreased. Increasing both will not give a positive change, or either it will go as no change or it may cause a decrease in your mass transfer coefficient compared to the initial mass transfer coefficient. Now, question number 3. Hydrogen has been studied extensively for use in monopropellant thrusters for space flights of long duration. Thrusters are used for altitude control of communication satellite. Here, the decomposition of hydrogen over a packed bed of alumina supported iridium catalyst is of interest. In a proposed study, a 2% hydrogen and 98% helium mixture is to be passed over a packed bed of cylindrical particles of 0.25 centimeter in diameter and 0.5 centimeter in length at a gas velocity of 15 meter per second and at a temperature of 450 Kelvin. The kinematic viscosity of the helium at this temperature is 4.94 into 10 power minus 4 meter square per second. The hydrogen decomposition reaction is believed to be externally mass transfer limited under these conditions. If the packed bed is 0.05 meter in length, assuming isothermal operation, the conversion is 100% for a porosity of 0.3 and DAB of 0.69 into 10 power minus 4 meter square per second at 298 Kelvin. Now, this problem is same as a problem that was solved in lecture 30. So, initial part of it is the same. Now, they have asked for estimate the conversion using both Theonis-Kramer and Colburn correlation if the bed porosity is changed from 0.3 to 0.4 and your uh, superficial velocity is 150 meter per second and your temperature is 450 Kelvin. Sorry, here the original temperature in which was solved in the class is 750 Kelvin, whereas the change in temperature they have given as 450 Kelvin. Okay, if the cylindrical catalyst particles are replaced, and the case 2 is cylindrical catalyst particles are replaced by spherical catalyst particles of diameter 0.25 centimeter, and again here in the second case also the velocity is 150 meter per second and the temperature is 450 Kelvin. That is we just so compared to the original problem they have changed your gas phase velocity from 15 meter per second to 150 meter per second. That is, it has become 10 times. While your temperature, sorry, I'll just change. While your temperature is decreased from 750 to 450 Kelvin, and your porosity of the bed is again increased to zero point 0.4. That means porosity of the bed means if the particles are placed, the gap between the particles, it causes pores, right? So that porosity is what is given, which is increased to zero point 0.4. Now they have asked, under these changes for the same cylindrical catalyst, what will be the conversion? And in the second case, for the same condition of porosity of zero point 0.4 and 150 meter per second of gas velocity and temperature of 450 Kelvin, what if we replace a cylindrical catalyst by a spherical catalyst? What will be the conversion? Now we have to solve these two problems using both the correlations. One is the Thiernes-Kramer correlation and the second one is the Kolben correlation. Now let's start solving the problem. Now case 1. So your conversion is given by x is equal to 1 minus exponential of minus kc into AC into L by U, where your kc is your mass transfer coefficient, AC is surface area per unit volume of the bed, and L is the length of the bed, and U is your superficial velocity. Now given U is equal to 150 meter per second, and then your porosity is 0.4. Now they have given DAB at points at 298 Kelvin. Now how to find the next is the diameter of the catalyst is 0.25 into 10 power minus 2 meters, and your length of the catalyst is 0.5 into 10 power minus 2 meters, and your kinematic viscosity is 4.94 into 10 power minus 4 meter square per second, and temperature is 450 Kelvin. Now what we have to find, since they have given the diffusivity at 298 Kelvin, now we have to find out the diffusivity at 450 Kelvin. So assuming a Knudsen diffusion, because this is flow through some constriction, right? So we assume a Knudsen diffusion. So your diffusivity correlation with respect to temperature is DAB at temperature T2 is equal to DAB at temperature T1 multiplied by T2 by T1 power half. Now substituting that, so DAB at 450 Kelvin is equal to DAB at 298 Kelvin, which is nothing but 0.69 into 10 power minus 4 multiplied by T2, which is 450 Kelvin, by T1, that is 298 Kelvin whole power half. So if you observe, the value is 0.85 into 10 power minus 4 meter squares per second. So when the problem was solved in the class at 750 Kelvin, the DAB at the diffusivity at 750 Kelvin was somewhere around 3 it was around 3.6 into 10 power minus 4 meter square per second, whereas when the temperature reduces by 300 Kelvin from 750 to 450, now we can observe there is a significant change in your diffusivity as well. So it has become to 0.85. However, there is an increase compared to your 298 Kelvin, the diffusivity at 298 Kelvin. Now further, now with the available information, we can initially find out what is your Schmidt number. Schmidt number is nothing but your ratio of momentum diffusivity to mass diffusivity, or it is the ratio of your kinematic viscosity to your what is it? It is your kinematic viscosity to your diffusion coefficient DAB. So substituting the values of both, you will end up with your Schmidt number is equal to 5.8. Now, your Schmidt number. So, what is Theonis-Kramer correlation? Theonis-Kramer correlation is, you know, modified Sherwood number is equal to 1 into modified Reynolds number power 0.5 into Schmidt number power 1 by 3. So there is no change. If you just observe, there is no change with respect to your Schmidt number. It is the same Schmidt number in the Theonis-Kramer correlation you are going to use, because it is Schmidt number is nothing but your ratio of your properties only, your kinematic viscosity to uh, your diffusion coefficient. Whereas the other terms, it has your flow behavior and your flow related terms. Now, since it is a cylindrical pellet, because they have given it as a cylindrical pellet where they have given the diameter of the pellet is 0.25 into 10 power minus 2 meters, and your length of the pellet is 0.5 into 10 power minus 2 meters. Now we have to find the equivalent diameter, because this Theonis-Kramer correlation is for for a spherical catalyst. Now, so we have to convert your diameter to a the diameter and length to an equivalent diameter. So if if we replace the cylindrical catalyst by some equivalent spherical, so it will, so assuming that there is an equality in volume, and then we find out what is the equivalent diameter. So your equation becomes dp is equal to 6v by pi whole power 1 by 3. That is nothing but 6 into, what is the volume of the cylinder? It is pi d square into L. So pi d square into LP, volume of your cylinder is pi d square into LP by 4. So substituting that, you will end up with 6 into pi d square LP by 4 multiplied by 5 multiplied by pi the whole power 1 by 3. So your pi and pi cancel out. So you will end up with 6 by 4 into d square LP whole power 1 by 3. So substituting for your diameter and length of the cylindrical particle, so you will get 6 by 4 into 0.25 into 10 power minus 2 the whole square multiplied by 0.5 into 10 power minus 2 the whole power 1 by 3. So you will end up with the diameter, equivalent diameter for the case of cylindrical pellet is equal to 3.61 into 10 power minus 3 meter. Now we have to find out your Reynolds number. Your Reynolds number is given by U into dP by nu, where U is your superficial velocity, superficial gas velocity, and dP is your particle equivalent particle diameter, that is equivalent diameter of the cylinder, divided by nu, where nu is your kinematic viscosity. So you have values of all the terms. So where your U is equal to 150 and your particle diameter, equivalent diameter, just now we calculated, which is equal to 3.61 into 10 power minus 3 meter, divided by kinematic viscosity is also given, which is 4.94 into 10 power minus 4. So you will end up with your Reynolds number as 1096.15. So now we have to find out what is the modified Reynolds number. So modified Reynolds number is given by based on porosity of the bed and the shape factor. So modified Reynolds number is Re prime is equal to Re divided by 1 minus phi into your gamma, where phi is your shape factor and phi is your porosity and gamma is your shape factor. Now how do you find this shape factor? So shape factor is your curved the surface area available divided by the equivalent surface area of a sphere. Okay, so that will give you gamma is equal to 2 pi RL, that is your curved surface area of the cylinder plus your surface area of the edges, which are circles, right? So plus 2 pi r square. So 2 pi RL plus 2 pi r square divided by pi d square. So we have all the terms, right? Are you have, so they have given the diameter of the pellet, they have given uh, uh, which is nothing but your 0.25 centimeters. So your radius is going to be 0.125 centimeters, and your length of the particle is also given 0.5. So substitute, and you have the equivalent diameter also, where this dp denotes the equivalent spherical diameter, which is dp, which is also calculated, which is equal to 3.61 into 10 power minus 3 meter. So substituting all the values, you will get the shape factor as 1.2. Now we have the Schmidt number. So substituting for the the terms in the modified Reynolds number, you have modified Reynolds number is equal to Reynolds number by 1 minus 5 into gamma. So 1090, so where your Reynolds number is 1096.15 divided by 1 minus your porosity is 0.4 multiplied by shape factor 1.2. So you will end up with your modified Reynolds number as 1522.43. Now we have to find out, we have found out what is the Schmidt number, we have found out what is the modified Reynolds number. Now we have to incorporate these two into the Sherwood number formula, that is the Thienes-Kramer correlation. So your modified Sherwood number is 1 into modified Reynolds number power 0.5 multiplied by Schmidt number power 1 by 3. So substituting the values, you will get your Sherwood number is 70.1. Now we have to express what is your the Sherwood number in terms of your mass transfer coefficient, because ultimately we have to find out what is the mass transfer coefficient in order to find out your conversion. So the mass transfer coefficient is given by, so here it is the modified Sherwood number. So you have your porosity and shape factor components coming into the formula as well. So your mass transfer coefficient is given by modified Sherwood number multiplied by your it's multiplied by DAB by DP into 1 minus 5 by 5 multiplied by gamma. So substituting all these, you will get Kc is equal to your modified Sherwood number is 70.1. Your diffusivity is 0.85 into 10 power minus 4. Your equivalent diameter is 3.61 into 10 power minus 3. Your porosity is 0.4. So 1 minus 5 is 1 minus 0.4 divided by 0.4 multiplied by your shape factor 1.2. What do you observe? Your Kc is equal to 2.97 meter per second. So now we have to find out what is the surface area per unit volume of the bed. So surface area per unit volume of the bed, it has to account for both the it has to account for your porosity also. So your porosity is 0.4. So the actual surface area available will be a factor where you multiply 1 minus of your porosity where the actual particle is. So you will get the value, the formula as AC is equal to 6 into 1 minus 5 by dP. So 6 into 1 minus 5, 5 is 0.4, so 1 minus 5 is 0.6. So 6 into 0.6 by dP, your equivalent diameter is 3.61 into 10 power minus 3. So you will end up with surface area per unit volume of the bed as 997.23 meter square per meter cube. Now we have to substitute. We have your mass transfer coefficient, we have the surface area per unit volume of the bed AC, we have the length of the bed, which is nothing but 0.05 meters, and we have your superficial velocity 150. So substituting all these terms, you will end up with what is your conversion. So conversion is equal to 1 minus exponential of minus Kc AC into L by U that is equal to, so 1 minus exponential of minus 2.97 into 997.23 into 0.05 by 150. So you will end up with your conversion as 0.63. So what can you observe from this? So when your superficial velocity there's a 10 times increase in the superficial velocity to what is given in the initially, that is, initially it was 15 meter per second. Now it is 10 times, so 150. So obviously one would think, there is a significant increase, there must be significant increase in your reaction rate and subsequently your conversion. But it didn't really result, because there is one more factor. There are two more factors. One of the critical is your temperature. Your temperature has changed from 750 Kelvin to 450 Kelvin, and your bed porosity has changed from 0.3 to 0.4. So this has made the conversion from 100% conversion to only 63% conversion when we calculate using your Theonis-Cramer correlation. Now let's see what do we get based on the Kolben correlation. So what is it? Kolben correlation is given by phi into JD is equal to 0.765 by Reynolds number power 0.82 plus 0.365 divided by Reynolds number power 0.386, where phi is nothing but your porosity. JD is your Kolben factor. And here your diameter will become square root of AP by pi, where AP is again your available surface area, which is given by pi dLP plus 2 pi d square by 4. So substituting, we already have the data for diameter and your length of the catalyst pellet. So substituting these, you will get your diameter as 3.95 into 10 power minus 3 meter. And so the Schmidt number didn't change, because none of the properties related to Schmidt number changes when we change the correlation, whether it is going to be a Theoner-Cramer correlation or whether it is going to be a Kolben correlation. The Schmidt number is not going to change. Only there will be a difference due to your Reynolds number, because your equivalent diameter is getting changed. The formula for equivalent diameter is getting changed. So finding out what is now the Reynolds number. Reynolds number is U into dP by nu. So you have, we have calculated what is the equivalent diameter in this case. So we can find out what is the Reynolds number. So you will end up with the Reynolds number of 1199.39. So substituting this in the Kolben correlation, you will get phi JD is equal to 0.026. So your Kolben factor is 0.065. So we have all these. So substituting it, so Sherwood number is given by, Sherwood number is equal to JD into Reynolds number into Schmidt number power 1 by 3. So Sherwood number is 0.065 into Reynolds number, which is calculated to be as 1199.39 into Schmidt number is 5.8 power 1 by 3. Substituting this, you will end up with a Sherwood number of 140.07. So with the Theonis-Cramer correlation, we found out the modified Sherwood number was nearly 70. Whereas here with this correlation, we find the Sherwood number as 140. Now we know the correlation. So Sherwood number is Kc into dP by dAB. So rearranging it, we get Kc, which is your mass transfer coefficient, is equal to Sherwood number into dAB by dP. So substituting the values, so Sherwood number is 140.07 multiplied by your DAB, which is 0.85 into 10 power minus 4, divided by DP, which is the equivalent diameter, that is 3.95 into 10 power minus 3. So you will end up with the Kc of 3.01 meter per second. So again, the surface area per unit volume of the bed is going to change because your equivalent diameter in this approach is different. So again, you're calculating what is AC. So AC is equal to 6 into 1 minus 5 by dP. So 5 is 0.4. So 1 minus 5 is 0.6. And your dP is 3.95 into 10 power minus 3. So substituting the values, you will end up here with the area is equal to 911.39 meter square per meter cube. So substituting those in the conversion expression. So conversion is 1 minus exponential of minus Kc AC into L by U. So substituting it, so 1 minus exponential of minus 3.01 into 911.39 into 0.05 by 150, you will end up with a conversion of 0.6. So there is a difference in conversion obtained using Theonis-Cramer correlation and your Kolben correlation. So Theonis-Cramer gave 0.63, whereas here it is 0.6. There is a minor difference is there. Now case 2. We are replacing the cylindrical particle, catalyst particle by a spherical catalyst particle. So again here expression for your conversion is not going to change. So conversion x is equal to 1 minus exponential of minus Kc AC into L by U. It is not going to change. So again U is 150 meter per second. Your phi is 0.4. And your DAB at 298 is 0.69 to 10 power minus 4 meter square per second. And now the diameter of the catalyst is 0.25 into 10 power minus 2 meters. Next, your kinematic viscosity is 4.94 into 10 power minus 4 meter square per second. Temperature is 450 Kelvin. Now, the same, DAB at your diffusivity at 450 Kelvin. It is again not going to change as the previous case. So, it is going to be 0.85 into 10 power minus 4 meter square per second. Again, your Schmidt number is not going to change as your kinematic viscosity and DAB for both the cases are the same. So, you will end up with the same Schmidt number, which is nothing but 5.8. Now, Theonis-Cramer correlation for this case too. So, your modified Sherwood number is 1 into modified Reynolds number per 0.5, Schmidt number per 1 by 3. So, now we have to think, should we use any equivalent diameter? No, right? Because here we are going to use a spherical particle itself. So, there is no calculation of equivalent diameter. So, whatever diameter of the catalyst pellet is given is going to be the diameter which you are going to use for the estimating the Reynolds number. So, your Reynolds number is U into dP by nu. So, U is given 150 and your diameter of the particle is 0.25 centimeter, that is 0.25 into 10 power minus 2 meter. Substituting that value by nu, the value of nu is nothing but 4.94 into 10 power minus 4. So, here you will end up with your Reynolds number as 759.1. Whereas in the first case of a cylindrical pellet, for your Theonis-Cramer correlation, your Reynolds number was around 1000. Here it is 759. And then you have to incorporate modified Reynolds number. Your modified Reynolds number is Reynolds number into 1 minus 5 into gamma, where gamma is a shape factor. Now, what will be the shape factor? Your shape factor for this case, the shape factor is mainly determined for a non-spherical particle. So, for a spherical particle, your shape factor is nothing but equal to 1. And you already have what is your phi, which is nothing but your porosity. So, substituting that, you will get your modified Reynolds number as 1265.17. Now, incorporating the values of modified Reynolds number and Schmidt number, you will get your modified Sherwood number as 63.91. So compared to your cylindrical particle, now when calculated for a spherical particle, you find that your modified Sherwood number is 63, whereas in the previous case it was 70. Okay, now let's see what is this impact on the conversion. Okay, now again your Kc is equal to your modified Sherwood number into your diffusivity divided by particle diameter into 1 minus 5 by 5 into your shape factor. So substituting the values, you will get your Kc is 3.25 meter per second. So there is an increase when all other parameters are same, but only your particle is changed from a cylindrical pellet to a spherical pellet. So there is an increase. So if we just observe, sorry. So in the cylindrical pellet, it was 2.97 meter per second for Thiernes-Kramer correlation, your mass transfer coefficient. Whereas for the spherical pellet, it is 3.25 meter per second. Now, again, we have to find out what is the surface area per unit volume of the bed. Here again, we have to use the diameter of the particle, which is nothing but, which is actually given, which is 0.25 into 10 power minus 2 meters. So, substituting that, you will get your surface area available is equal to 1440 meter square per meter cube. So, we could find out that the surface area has increased because the equivalent diameter considered obtained for a cylindrical pellet was higher than that of the diameter of the spherical pellet, which is given, right? Because the equivalent diameter calculated was about 3.61 into 10 power minus 3, that is nothing but 0.36. Here it is 0.25 into 10 power minus 2. So there's a, when the particle size is decreasing, your surface area available, it has increased. So your conversion is, substituting all the parameters, you will find out your conversion is increased. In this case, it is 0.79, whereas in the previous case, it was around 0.6. So there is an increase when you change the particle from a cylindrical particle to a spherical particle, right? So next, through Kolban correlation. So your Kolban correlation, again it is 5 into JD is equal to 0.765 by Reynolds number power 0.82 plus 0.365 by Reynolds number power 0.386. Schmidt number is 5.8. So here again, your Reynolds number is going to be the same as one calculated for your Thiernes-Kramer correlation. Why? Because it is only the spherical particle. Again, here again, there is no no need of calculating any equivalent diameter. So in both the cases, your Reynolds number is going to be the same, 759.1. Now, further substituting the values of the Reynolds number, you will end up with your Kolban factor as 0.079 and your Sherwood number is equal to JD into Reynolds number into Schmidt number power 1 by 3. So, you will end up with Sherwood number as 107.75. And your mass transfer coefficient is Sherwood number into diffusivity divided by your particle diameter. So substituting that, you will end up with your mass transfer coefficient as 3.66 meter per second, right? And your area is again not going to change. So surface area available per unit volume of the bed is not going to change because there is no change in diameter. Further, both the correlations. So your AC is 1440 meter square per meter cube. So substituting it in the expression for your conversion, you will get conversion as 0.83. So we are just tabulating, all the data. So for the case 1 cylindrical pellet, your Theonos-Kramer gave conversion of 63%, whereas your Colburn correlation gives conversion of 60%. Whereas in the case 2, your spherical pellet, your Theonos-Kramer correlation gives 79% conversion, whereas your Colburn correlation gives 83% conversion. So if we compare both case 1 and case 2, of course, when we change it from a cylindrical pellet to a spherical pellet, for this case, one clear observation is that there is an increase in conversion. However, both the correlations are giving slightly different values. But one more observation if we could see, even though the superficial velocity has increased by 10 times for the cylindrical pellet case which was solved in the class, we could find out the conversion has decreased significantly. Where initially there was a 100% conversion, now the conversion has drastically reduced. Where for the cylindrical pellet it is 63%, and in case of a spherical pellet it is approximately 80% conversion. So this may be due to the factor of the major factor of the temperature, because you could find the drastic difference in the diffusion coefficient also, and there is a minor change in your porosity of the bed also. So your increasing the velocity by 10 times really didn't help in conversion, right? So we have to consider all the parameters while considering the conversion, because just increasing the velocity, the superficial velocity to a greater extent may not help. So it may be due to several other factors. Now let's go on to the next question. Identify the external diffusion control zone and the surface reaction control zone in the below figure. So the below figure gives the reaction rate as a function of your superficial velocity to your diameter of the particle power half. And initially there is an increase, then beyond a certain point it becomes the reaction rate becomes kind of constant. So which part of it denotes the external diffusion control and which part of it denotes the surface reaction control? We have to identify that. So the answer is this. So your initial increase, your linear region, it denotes your external diffusion limitation, whereas beyond a certain extent of your velocity and diameter of the particle, it becomes independent of them and your reaction rate becomes constant. So when we just consider the previous question and think over it with this correlation, so it might be a chance that the velocity has the correlation with the velocity has at most got saturated, and that is the reason. So uh, uh, you know the reaction rate might have entered a zone where either it is external diffusion limited plus reaction rate limited, or it is only reaction rate limited. So we have to consider all the parameters while actually considering the conversion of the reactor. Okay, that's it with the questions. Thank you. So I thank you for the session. So we'll have the next live session on next Saturday at 4 p.m. Thank you all.